Hello. Today I will present my final project, which was done as a part of 15663 computation photography class. My project is titled as Intrinsic Image Decomposition for Downstream Image Coloring and Retexturing Tasks. The main motivation behind this project was this recently published paper called Intrinsic Image Decomposition via Ordinal Shading. Intrinsic image decomposition of an image is a process by which we separate an image into an illumination dependent component called shading and an illumination independent component called albedo. These decompositions can then further be used for other image editing tasks like recoloring, relighting, and retexturing. So this is a data-driven method, and before diving deep into how the method works, I just wanted to explain why it's difficult for data-driven methods to do this. As already said, shading is the illumination dependent component. Therefore, shading is heavily influenced by complex nature of lighting in a scene, including direct and indirect illumination, varying light sources, and shadows. Predicting shading accurately requires a model to capture this very complex different lighting scenarios, which can be a very difficult task for a data-driven method. So estimating shading directly from neural networks is not very straightforward, and the main challenge is the fact that most natural scenes have specular objects present in them, which leads to the illumination taking a large range of values. This results in a long tail distribution of values. One solution to this problem is to formulate the shading in a logarithmic scale. This leads to a more uniform distribution of values, but the logarithmic domain lacks contrast and a well-defined range. Using inverse shading solves these two issues. The contrast is preserved, and we have a shading range between 0 and 1, making it easier for the neural network to learn these values. We also have to somehow incorporate the scale invariant nature of the model. Since it is hard to estimate dense shading values, they use a more relaxed formulation of direct shading estimation, which basically means that the network is not tasked to predict the final shading values. Instead, it's only tasked to learn the relative ordering between shading values. This is done by making sure that a scaling and a shift in the shading produced relative to the ground truth still results in a zero loss. Now let's look at the method. There is a two-step approach to solve the intrinsic decomposition problem. In the first step, we estimate the ordinal shading values, which are generated at two resolution, at a receptive field resolution and at an original higher resolution. Since it is at a receptive field resolution, there the shading produced has global coherency, and the ordinal shading network is able to produce accurate ordering of the shading values across the entire image, which is a good starting point for our final dense shading estimation. The final prediction is generated at a higher resolution, which lacks global coherency, but it contains the local detail discontinuities. We use both these resolutions to finally use them as an input to the intrinsic image decomposition, which gives us the final shading values, and from that we calculate the albedo values. This has become an easier task for the intrinsic image decomposition because the network does not have to reason anything about the global structure like illumination direction or geometry, as it comes from the smaller resolution image, and it does not have to worry about the local discontinuities because that information comes in the higher resolution image. So all the network has to do is simply adjust the values of the lower resolution image while including some of the discontinuities in the higher resolution image to finally get to something that satisfies the intrinsic decomposition model. I also looked at their dataset, which contains a lot of indoor scenes, and then I tried to do the decomposition on several images that I thought could be a little bit out of domain. As you can see, it still works really well on faces, on these colorful pebbles, and on these paprikas. I then tried to use segment anything masks to recolor the object. As you can see, this is a better recoloring than if I were to recolor only the input image. There were some problems that I noticed, especially around the regions where there were high specularities and shadows. I captured my own scene of a metallic cup and a matte cup. So the shadows I think are still preserved really well, but the metallic part is not. I tried to recolor the metallic cup here again using segment anything model. As you can see, this does not look quite well. I want to propose another method where before doing the ordinal shading, I want to add a specularity removal part which can then give me a specular mask, which I can then apply to the higher resolution image, and then use all these three to produce a specular mask, a shading, and an albedo. Thank you.